Okay, great. So our second speaker in this session will be Ezra, and he will talk about why general graphs are easier than bipartite graphs. So please.
Okay, hi, I'm Tomer, and I'm going to talk about the secretary problem in under matching feasibility constraints. And this is a joint work with my PhD advisor, Michal Feldman, with me, Gravin, and with Zhihao, Tang. So you all know the secretary problem. We have, in general, we have n arbitrary values that are chosen by an adversary, and they are unknown to the decision maker. And they arrive in a random order, and the decision maker needs to decide upon each arrival whether to accept or reject the value that this is currently. And the decision must be immediately and irrevocably. And the goal of the decision maker is to pick the maximal value. And we measure the performance of an algorithm by the term competitive ratio, which is the expectation of the algorithm divided by the optimum offline. And a classical result shows that it is possible to achieve a competitive ratio of 1/e, and this is tight. And in this talk today, we're going to extend the problem of the secretary problem to matching feasibility constraints under two model of arrivals, vertex arrival and edge arrivals, which I'll define shortly. So let's start with the vertex arrival. So in vertex arrival, like it was already studied by Kesselheim et al., you have the simplest model of vertex arrival. You have a bipartite graph. You can think of one side as items, which is a static, and one side that is the agents that arrive online. And you have weights on the edges that are chosen by the adversary. And the agents arrive one by one. And each time that the agent arrives, we need to decide whether to match it to some item or whether to not match it at all and leave more items available. And our goal is to find a maximal matching. And Kesselheim et al. Showed that it is possible to achieve the same guarantee as the secretary problem of 1/e. And of course, we cannot do anything better because the classical example of the secretary problem also holds for this setting. And the question that we're trying to think of is what happens if both agents and items arrive online. So you have arrival of vertices from both sides, or even more generally, you don't have the bipartite structure anymore. And you have general graphs, and so you have a general graph, and vertices arrive online. Now you don't have sides anymore. So for example, first the right bottom, then the top left, and so on. And upon the arrival of a vertex, we need to match it to some vertex that already arrived and is available. Okay? And the goal again is to find a maximal matching or approximate the maximal matching online. So this is in the vertex arrival model. And the edge arrival model is defined similarly, but now instead of vertices arriving online, we have that the edges arrive online in a random order. And again, we need to commit upon each arrival of an edge whether to match it. If both vertices are available, we are allowed to match it. And again, the objective again is to find the approximate maximal matching. OK. So now that we defined the two problems that we are trying to solve, so what was known before? So I mentioned that the result of Kesselheim et al., the competitive ratio of 1/e. And the classical result of the secretary problem shows that you cannot do better. And for the edge arrival, Kesselheim et al. Showed that it's possible to achieve 1/2e. And again, the classical example also is an upper bound on what you can achieve. And we show that for general graphs, when all vertices arrive online, you can achieve actually 5/12, which is better than the 1/e, very surprisingly. And also, we improved the constant for the edge arrival, and we showed that it's possible to achieve 1/4 instead of 1/2e. In this talk, I'm going to focus on the positive results, although the hardness result is the most technical part of the paper. I will show today the two algorithms and their analysis, the main ideas for the analysis. So let's start with the vertex arrival for general graphs. So the first assumption that I'm going to make, which is without loss of generality, is that for every subgraph of even size, there is a unique maximal perfect matching. So if, for example, we have this graph, so of course there isn't a unique maximal matching, and it might even not be perfect matching. So what we do in order to have this assumption is we first make the graph full by adding just all edges with a weight of 0. Okay, this will guarantee that there is always a perfect matching which is maximal. And for the uniqueness, what we'll do is that we will perturb all the values by adding a small random variable. Okay, and we can do it, like simulate it online. If we see some graph, we can imagine that we see the modified graph, and it won't change. Like we can run it on and simulate it on the modified graph, and the results will all the same. And we don't change the optimum offline except for the perturbation, which is negligible. Okay, so with this assumption, now let's go to the algorithm. So the algorithm is divided to two parts. First, exploration, then exploitation. So in the exploration, we just ignore the first k vertices and don't match anything. And let's call this phase, let's denote by k the number of vertices that we don't do anything. Then, in the exploitation phase, what we do is, upon the arrival of a new vertex, the first thing we do is we calculate the unique max weight matching that of the vertices that arrive so far. And this we can do by the assumption that we just showed. And to be more accurate, like if I is odd, and then we have an odd number of vertices, so we don't have a max perfect matching. So what we actually do is remove a random vertex and do it on the vertices that are not without the random removed vertex for this step. And after we calculate the unique maximum weight matching, we find the partner of VI in this matching that we found. And if it's available, then we just match them. Okay, so this is a very straightforward algorithm. We just, every step, calculate the max weight matching, find the partner of the current vertex that arrived, and match it if it's available. Okay, so let's continue to the ideas in the analysis. So by the assumption, we can assume that in each round we have a unique maximal perfect matching. And because of you have always a unique maximal perfect matching, we have kind of a symmetry property, which means that each vertex will be available with the same probability. If we take the randomness upon the, if we calculate this probability over the arrival order of the vertices arriving so far. Okay, so all vertices that arrived so far have the same probability of being matched or not matched. And moreover, this probability is just a very simple function of the sampling phase and the time. So the probability that the vertex V will be available at time I is just 1/3 plus 2k cubed over 3i cubed, okay, approximately, up to negligible terms. And this is exactly the probability that will match VI, because we match it if his partner is available. Okay, so this is one part. And the second part is we want to bound the expected value of the current edge that we are trying to match, and we do so in two steps. The first one is that the expected maximal matching at step I, so we calculate maximal matching of the vertices 1 to I, and its expected weight is at least I square over n square times opt. And the reason for it is just that if you take an edge in opt, the probability that it arrived by time I is proportional to I square over n square. Okay, so, and this holds for every edge. Therefore, if we only count the matching that is the intersection of the optimal matching with the edges that arrive so far, we'll get I square over n square opt, and the maximal matching will be even better. Okay? So this is the weight of the maximal matching. And the weight of the edge that we're trying to match is just a random edge among these edges. So there are I over 2 edges in the matching of the first I vertices. So if it's just one random edge among them, so we get that if we match this edge, we get an expectation 2I over n square opt. Now if we try to combine everything together, the competitive ratio of the algorithm is just summing over the exploitation phase, the probability that we match, times the bound that we have for the fraction of opt that we get if we match this edge. And if we optimize this expression, we get that the best thing to do is to choose k equals n over 2, which leads to the competitive ratio of 5 over 12. And that's it. Let's move on to the edge arrival. So our algorithm will be very similar, but with a small tweak. So again, we have an exploration phase of, and the optimal exploration phase, again, is to weight m over 2. And what we do in the exploitation phase, and m is the number of edges. And now we don't need a tweak of just adding the 0 edges and perturbing. We do need a perturbing, but not the adding the edges. So in the exploitation phase, what we do is we first calculate xt to be the probability that both endpoints of ET are unmatched at this time. Now, this probability that we calculate is taken over both the randomness of the arrival order so far and also the randomness of the algorithm. And if we calculate this xt, which is a very difficult task, it's like doing it requires to go over all the suborders so far and like calculate expression that depends on for each suborder. So calculating xt takes exponential time, but let's assume that we calculate it. And then what we do with this xt is we, again, calculate mu t to be the maximal matching up to time t. Then if et, the current edge, is available and is in the maximal matching up to time t, then we, instead of matching it like we did in the vertex arrival, we just match it with some probability, which is a function of this xt that we calculate and the time t. OK, so let's go into the analysis. So very similarly to the case of the vertex arrival, you can show that the expected weight of mu t is proportional to the number of edges that arrive so far, which is 2i over mn. So the expected weight of mu t is approximately 2i mn over mn opt. The probability that we match ET is we need two things to happen. First, that it will be available, which is by definition xt. And then if it's available, we match it, if it's in MUT, in f, x, t, and t. So, so we want to choose f, x, t, comma, t to be something of the form 1 over xt times some constant or some expression, because we want to cancel out the xt term which depend on the edge and on the structure of the graph. And the best way to do so is like we want on one hand this expression to be as large as possible because it will guarantee a better competitive ratio. On the other hand, we don't want it to be too large because then this expression will be above 1. And if you remember from the algorithm, we need to select with this probability. And the probability must be at most 1. So for the algorithm to be valid, we need the expression to be always at most 1. And we show that if we choose this constant to be m squared over 4t squared for the sampling phase of m over 2, then this expression is always at most 1, and this is the main difficulty of the proof. Now combining everything together, like this choice of f x of t, so we get the competitive ratio is again the sum over all the times from m over 2 plus 1 to m of the probability that we match, which is m squared over 4t square, which the xt is cancels out, times the expectation of the weight of et, which is 2i over mn times opt. And this sum is can be simplified, or at least when taking m and m going to infinity, to be 1 over 4. OK. So this is regarding the edge arrival. So let me just summarize. So we have two natural arrival models for the problem of secretary problem with matching feasibility constraint. We show the positive result for the 5 over 12 competitive ratio for the case of vertex arrival. And in the paper, we also have a matching upper bound. And we know that the lower bound, at least if we don't bound the computational, if you don't take computational aspects, it's possible to achieve 1/4 competitive ratio in the edge arrival. We also generalize in the paper the result of the edge arrival to hypergraphs. And two open questions that remain from this work is one, first, is closing the gap for the case of edge arrival, which like both in secretary problem and also in the profit problems with matching and edge arrival, like there is a gap in edge arrival and in vertex arrival, it is closed. And closing it is a very important and interesting problem. And the second thing is finding a polynomial time algorithm, at least for the case of edge arrival. And that's it. Thank you.
Thanks, Thomas. Do we have questions?
Yes.
I didn't get how the general graph problem is not more general than the bipartite graph problem.
So it sounds more general. And indeed, for example, the former work we did was in the case of profit, and there it's more general. It's all like it's trivial. It's harder. But now, because all the vertices arrive in the random order, then the hard instance, at least for the vertex arrival in the two-sided, you have one static vertex, and we have n online vertices. And now that the static vertex will also arrive online, it helps you, because if it will come very late, like if you come in the end, you get the optimal solution for free. Okay, so it really helps you that the static side help. You cannot incorporate the case of the classical secretary problem.
But couldn't you, I mean, so in the bipartite case, isn't the right-hand side is kind of there at the beginning, right?
One side is static, yes, and one side arrives online.
But why can't you just simulate the online arrival by just, if you take your algorithm, go back to the static case and just kind of pretend you have it at the beginning, just pretend that it shows up later. I guess I'm missing how a simulation argument doesn't work.
So if you wait, so what we do is like wait half of the vertices, and then you can think of them as static. But you missed the potential of matching those vertices. So first of all, this is not, but this is not contributing to the claim. But for the now you have more flexibility because like the static side is random. It's not adversarial chosen. So this is what you're gaining. Yes?
The 1/2e result you mentioned, it's not polynomial type?
I don't remember. I don't remember whether it's okay. Yes?
What do you conjecture the tight guarantee is in the edge arrival case?
I suspect that it's less than 1/e. I'm not like doesn't sound that 1/4 is the optimal thing, but the 1/4 is tight for this type of analysis. So you won't get better with this same algorithm, just changing the parameters.
I maybe have one quick question and a quick answer maybe. Can you say a word about how you get the impossibilities, like that 5/12 is tight?
Mm-hmm.
Like just high level, the idea.
So yes, so like we have here why it's tricky to say that it's difficult to construct hard examples is that we are not in because we are in a multi-choice setting of secretary, we are not in the probability space. And our measurement is not the probability of selecting the maximal matching, because this is impossible to do. Like, you cannot get any constant. So we measure the performance in the expected, and the expected value compared to the value of the opt. And when you're in the value space instead of the probability space, like things are becoming much more difficult. And you need like multi-layer arguments to change from the probability space to the value space.
So you give a concrete construction of a hard instance, or?
We like to find the maximal edge. You cannot do with probability 5/12. Mm-hmm. So this is like the idea of why this is like if it's in the probability space, you would have an immediate argument why it's impossible. But
I see. And then
because
you
we're in the
reduce
value
that.
space, like everything becomes much more difficult.
Yeah. All right. Thanks.
Okay.
Yeah, let's thank the speaker again.